Welcome back from the break, everybody. So now we're going to have a look at all that we have learned in this session. We are going to summarize the atomic theory. So let's have a look at my screen. Summary. The first thing we need to note about atoms is that there is a very small center. That center is called the nucleus, and it is made up of protons, and protons are the positively charged particles. They're subatomic particles. And we have neutrons that are part of the nucleus as well. They are neutral. However, what they do have is mass. And so the mass of a proton and the mass of a neutron are the same. So these subatomic particles give the atom its mass. The mass is in the center. It is a very small part, and the protons and the neutrons together will give the nucleus its mass, the atom its mass. Now, the electrons, that's the other subatomic particle, is they were the first subatomic particles to be found, and they are negatively charged particles. And what they do to the atom is they give it its volume. So they are the particles that are whizzing around. They've got lots of energy. They are moving constantly, and they form the volume around the nucleus. They are the ones that will give us a radius. So the radius is from the center, so from the nucleus to the extremities of the electron's movement, and they will give the atom its radius, so its volume. Okay, so we did speak about that. We spoke about how tiny the atom was, that it has got a radius. Depending on what element it belongs to, its radius will be bigger or smaller. And that is determined by its atomic number. So the atomic number is the number of protons, and we denote that with a Z. So the Z tells us this is the atomic number. It is the number of protons. The number of protons in the nucleus determines the element that that atom belongs to. And if you look on the periodic table, you'll see hydrogen has an atomic number of 1. It means it's got 1 proton, and if it's a neutral atom, it's going to have 1 electron. And so we go along. I think oxygen is 8, and fluorine is 9. So those atomic numbers tell us that this atom is specific. It belongs to the element of fluorine or oxygen or hydrogen because of the number of protons it has in its nucleus. Now, not only does the number of protons add to the mass of the atom, but also the neutrons, as we have discussed. And so we have what is called a mass number. So the mass number is denoted by an A, a capital A, and it is the number of protons and neutrons together. And so if we get that format, so sometimes we have an element, we given its symbol, and we have the number A over there and the number of Z there, we can calculate how many protons the atom is going to have in its nucleus by working out Z subtract A. Okay, sorry, the other way around, A subtract Z, to give us the number of neutrons, or alternatively the number of protons. Okay, so let's move on. This has quite a big impact on the mass of the atom because the number of neutrons can change. So it doesn't affect the charge on the atom, the number of neutrons, but it does affect the mass. And so we have what is called isotopes. So there is a percentage of isotopes that we find within a sample of atoms of a specific element. And scientists have found that that is a set percentage. So this is the first thing about isotopes. There is a set percentage in nature of isotopes of a specific element. There aren't millions and millions of isotopes. We see that chlorine has got 2 isotopes and that hydrogen has 3 isotopes. So we're not going to find more than that in nature, and there is a specific percentage. And so what scientists have done is they've worked out an average mass for a sample of an element of atoms. And so this is taken into consideration when we calculate the relative atomic mass. That's what it's called, the relative atomic mass. That percentage of isotope is taken into consideration. We calculate the mass, and then we add them all together and we divide by the number of isotopes that we have. So we did do that earlier, so go back and look at that if you are struggling with this concept. So I spoke about here mole, so it is the average mass of a mole, and you will come across this word mole. It's just an amount, a set amount, so everything is constant. Our calculations are true and consistent. So you'll come across that word mole later on. So don't worry about that too much. Just know that it is a set number that we look at when we look at the percentage of isotopes. Okay, our next section that we looked at were the electrons and how the electrons are organized and layered around the nucleus of the atom. We spoke about energy states. So each electron has an energy state, an energy amount, we can call it. And so that will determine where those electrons are allowed to be around the nucleus. So that means that they reside in an energy level according to their energy states. Now, energy level, we spoke about very briefly, Niels Bohr, and what he did was, his theory is that around the nucleus we have an energy level number 1, and then we have the next energy level number 2, and so it goes, energy level number 3. Okay, so there is order to the way that the electrons are positioned or are allowed to be, and that depends on their energy state. So within each energy level, n equals 1, n equals 2, n equals 3, we find orbitals. Now the orbitals are telling us about the shape. In the shape, the volume in which those electrons will move. And the first one that we spoke about was the s orbital. It's spherical shaped, it's like a ball, and it would be like a filled ball. So the electron would be allowed to move all around in that space. The second orbital shape that we spoke about were the p orbitals, and we've got 3 of them. They are a figure of 8 or a dumbbell shape. We spoke about these ones. They look like that. And we've got them in 3 planes, the x plane, the y plane, and the z plane. So this is all 3-dimensional. It's quite difficult to get our heads around it. And so we do have pictures, 3D pictures, to help us see it. However, it's best if we use something called an electron configuration to write down what the electrons are looking like. Okay, drawing those pictures is really tedious, and if you're not an artist, it could be really disastrous. So we have, when we talk about electron configuration, we have 2 rules. We've got Pauli's exclusion principle, and that is telling us that the electrons have to spin in opposite directions. And that's why we show them as arrows, one pointing up and one pointing down, is to show us that the electrons are going to spin one this way and one the other way. And that's how they cohabit their orbitals. That gets over the repulsion. The second rule is Hund's rule, and Hund's rule really says that you can't start pairing electrons without first spreading them out into all the orbitals that are available as singles. Okay, so they like to be single first before they get joined by a partner. We could call it the singles rule, really. Okay, so let's have a look at how we configure the electron structure. It's called electron configuration. There are two ways. The first way is using the energy level diagram. Oops, my pen's not working so well. Let's do that. So the energy level diagram, the old name for it is the off-bow diagram. And you see we've got these blocks. These blocks represent the orbitals. The first energy level is the 1, the n equals 1, so 1s. There's the first energy level. Okay, I'm going to draw a line. We don't normally draw a line, but I want to show you that this is the first energy level. Then we have the second energy level, and we start off with an s orbital, and then we've got the two p orbitals over there. And remember, they are x, y, and z. You don't necessarily have to write this down, but it's just to show you why there are 3. Okay, so that would be the y would look like that, the x would look like that, and then the z is the one that sticks out in a funny plane like that. Okay, so that's the second energy level. Then we've got the third energy level, n is equal to 3. We've got the 3s orbital, that's the spherical one, and then we've got the 3p orbital. And again, those are x, y, and z. So we've got 3 of them. And the last one that you encounter is the 4s, because that's as far as you go. Okay, so this is not where the atoms stop or the elements stop. They do continue. We get into d orbitals and f orbitals, and it becomes quite hair-raising. So that's as far as we go for school level. So instead of drawing the energy level diagram, we can also write out the electron configuration in the SP notation. So it's sometimes called the SP notation. And what we do is, it's almost like a shortened version. We write 1s, and we know that a maximum of 2 electrons can fit in there. Then it becomes the 2s, a maximum of 2, 2p, a maximum of 6, 3s, a maximum of 2, 3p, a maximum of 6, and then obviously our last one would be the 4s, maximum of 2. So that is the other way of representing how the electrons sit around the nucleus of the atom. Right, everybody, that's all we have time for today. I hope that gives you a good idea of what our atoms look like. I will see you next time.